An example implementation of Butterworth analog filter is discussed in this video. As you can see, the circuit is implemented with 4 operational amplifiers or op-amps and a number of passive components including resistors and 2 capacitors with the same value C. There are 2 feedbacks. Aside from local feedback for each op-amp, there are 2 overall feedback. One is shown here via resistor R, and the other one is shown here via resistor R2. We want to see how the circuit is working and how we find the value of the components in the circuit so that we can achieve a target cutoff frequency, for example 500 kilohertz, which can be a different number depending on your target application. Okay, so let's make the assumption that op-amps are properly biased. So by properly biased, I mean the supply voltages, whether double supply or single supply, should be there correctly. And then also notice that we have the proper connection at the output of the op-amp via, let's say, a component like resistor or capacitor to inverting input or negative input terminal, indicating the existence of negative feedback locally for each op-amp. At the same time, the positive terminal for all op-amps, they are connected to just ground, so the voltage at the positive terminal is 0. Now, with the proper bias, so given the proper bias for op-amp, and given the negative feedback for op-amps, we can say op-amps are operating in linear region of operation, so op-amp in linear region, and as a result, I can say virtual short is valid for each op-amp, which means that the negative feedback enforces that the input terminals should have the same voltage, and because the positive terminal for all of the op-amp 1, 2, 3, 4, because their positive terminal is at 0 volt, therefore via virtual short we are guaranteed that the negative terminal is also at 0 volt. So I'm going to write 0 for the negative terminal for all the op-amps. This is going to help a lot with respect to quickly find the transfer function of this circuit, basically defining Vout as a function of input Vin. So let's focus on op-amp 4, which is in inverting amplifier configuration, and it's easy to see that the current that flows through R should flow through C, because nothing can flow through the input terminal of the op-amp that has practically infinite impedance. So from there it's easy to see that the, let's say, voltage at output of op-amp 3 V3, so at this node I can see that V3 minus, so I'm going to write it quickly here, V3 minus 0 divided by R, which is this current, should be equal to 0, this voltage, and then minus V out, which is therefore the voltage drop across capacitor C. So the voltage drop across capacitor C is therefore 0 minus V out divided by 1 over CS impedance of cap, which as a result of this we get V3 should be equal to minus RCS times V out. The voltage gain of the inverting amplifier basically. So this node is minus RCS times V out. Now the same thing can be done for the op-amp number 3, which is in the same sort of configuration, which is the negative, which is the inverting terminal configuration. As a result, I can do another multiplication, so I can multiply this whole thing with minus RCS again to get to V2, which is the voltage at the output of op-amp 2. So here we should have minus RCS squared times V out. Basically, again, I multiplied this whole thing with minus RCS, same as what I did for the 4th stage. Okay, so now we have voltage at V2 defined as a function of output, voltage at V3 defined as a function of output. Now I can focus on finding the voltage at the input, voltage at the output of the op-amp 1, which I refer to as V1. So I can just simply write a Kirchhoff current law, or KCL, the current that is flowing in that has no other way to go aside from this way should be equal to the sum of the 2 currents that are flowing out. So I can refer to this as, let's say, I1, and this one is I2, and this one is I3. So what I can say is writing a KCL at, let's say, a negative input terminal of op-amp 2, so I'm going to write it as negative, or let's say just refer to it as node let's say node minus 2. So I'm going to refer to this as node at minus for op-amp 2. So that is the negative input terminal of op-amp 2. I'm writing I1 should be equal to I2, and then should be equal to I2 plus I3. When I say the negative input terminal, I mean basically this node. So if we just substitute for these values, I1 is the current through this resistor R, which is simply the voltage drop V1 minus 0 over R, and I2 is the current through resistor R, which means 0 minus, as you can see, the other side of this resistor is connected to the output Vout, so therefore 0 minus Vout divided by R, and for I3 it's true resistor R here, so it's just simply 0 minus V2 divided by resistor R. These resistor R cancel out from both sides, and I get V1 is just simply minus Vout plus V2, which I can then substitute for them. So it's equal to minus Vout, and then for V2 I'm going to substitute from what I found here. So let me write it here as well. V2 is equal to minus RCS square Vout. So that is equation number, let's say 1, 2, and I'm using equation 2 here. So it's basically just R square, CS square, SS square, and I can factor out Vout. So I found V1 as a function of Vout. Let's refer to this as equation number 3. Okay, so the last thing I need to do is, now I need to just simply write a simple KCL at this node. So if I write a KCL, or again the Kirchhoff current law, the sum of, again, the incoming current should be equal to the sum of outgoing currents in this case. So another KCL, and this time at, say, negative terminal of op-amp 1. So input negative terminal, input negative terminal for op-amp 1. I can write the incoming current is basically just Vin minus 0 divided by R. The 0 is the voltage at the negative terminal, obviously, and equal to outgoing current, this current, which is simply 0 minus, you can see that on the other side is connected to V3, or that the output terminal of the op-amp number 3, which has a voltage V3, divided by, be careful, this is resistor R2, not R anymore, so R2, and then for this current, it's the current through R, so it would be 0 minus V1, so minus V1 divided by R. Okay, so in this case we have Vin, just reshuffling the values around, so we would get Vin equal to minus V3 plus R. So just one more thing, it would be Vin equal to minus V1 and plus R over R2 times V3. Now I can substitute equation 1. So equation 1 basically defines V3 as a function of Vout, this equation. So I'm going to substitute from that, and I get this. Vn is equal to, and at the same time also, let's do it at once. So I'm going to substitute from equation 3. So I'm going to use equation 3 here to substitute V1 as a function of, let's say, value of Vout, and I'm going to use equation 1 to do the same thing for V3. So combination of using equation 1 and equation 3 here. And I get Vin is equal to minus, so there's another minus here, it will cancel out, this minus here, but let's keep it so that I'll do it in another shot. So R square, CS square, SS square, and then minus R over R2. I'm just substituting V3 here, which has a negative sign as well. So that's why I wrote minus, and then we have RCS and Vout. So we are almost done. we found the transfer function, which is V out over V in, or the transfer function of this filter or this amplifier or this circuit is simply 1 over 1 plus R over R2 R square over R2 CS plus R square C square S square. And if we just reshuffle again things, so we get H of S, or the voltage gain of the amplifier, is 1 over R square C square divided by S square plus 1 over R2C S plus 1 over R square C square. So the benefit of finding the transfer function this way is because now if I just refer to as 1 over RC as omega C, and then if I also define R2 as R, the main resistor in the circuit. By the way, the resistor that we have in the input positive terminal is just for the better matching for the op amp and having less offset, practically speaking. So it's just there for practical reasons. Otherwise, this terminal is grounded. So we have, if we define R2 as R over alpha, then we can just write the circuit this way: H of S equal to 1 over S. So we have omega C squared S squared plus we have effectively alpha, given that I can substitute R2 with R over alpha and then 1 over RC is omega C, then I get alpha omega C S plus omega C squared. This is what I was looking for. This is what is getting close to Butterworth. So Butterworth, let's say, transfer function for a second order Butterworth filter. So the Butterworth filter general structure or format, let's say the frequency response looks like this for nth order Butterworth filter: 1 over 1 plus omega over omega C to the power 2n. So if we are interested in finding, say, second order Butterworth filter, so second order Butterworth filter, low pass filter, LPF, then basically we are saying n is equal to 2, and then the, let's say, magnitude response as a function of omega or radiant frequency becomes 1 plus omega divided by omega C to the power 4, because n is equal to 2. Okay, so this is what we are trying to realize in this circuit. And basically the look of the, let's say, the look of the frequency response or magnitude response is something like this. So if we show it, then at, say, target omega C, or the cutoff frequency, then the kind of the look of the let's say the magnitude response as a function of omega in radian per second would be something like this. So it starts at 1, and then it goes flat, and then it starts dropping or drooping, and then at frequency of omega equal to omega C, we get exactly 3 dB drop no matter what order we are targeting. And then this keeps going down, and depends on the order of filter, of course it will be sharper drop. So the level of drop or the sharpness of drop will depend on the order that is selected. But no matter what order we select, all of them cross this point. So if you go, for example, with say higher order, then you have, let's say, this response for the higher order design. So it crosses again at this point, 3 dB point, but then it drops faster for higher order design. This is the point that the frequency response is at, let's say, 0.7, or basically the drop for h omega square is at 1 over rad 2 to the power 2. So this is the point of the 3 dB drop, basically. That translates to 3 dB drop. So this effectively is 3 dB or cutoff frequency. So this is what we refer to as cutoff frequency or 3 dB frequency. And so at this point, we need to have this sort of a frequency response. If you take a look at what we got here, if we substitute S with j omega, we get h of omega equal to omega c squared divided by j omega squared, and then plus j alpha omega c omega, and then omega c squared. So if I'm interested in finding, say, the magnitude squared, then I get omega c to the power 4, and of course this one is negative omega squared, and then in denominator I have a complex number, so I need the squared magnitude of a complex number, which turned out to be omega. So omega squared, which is this one, doesn't matter the polarity of the negative sign here because it's raised to the power 2, and then this to the power 2. So plus alpha square omega c square omega square. Now if we let's say expand the denominator, what we get is this one. So again, numerator is omega c to the power 4. In denominator we have omega to the power 4 minus 2, let's say plus omega c to the power 4, and then we have minus 2 omega square omega c square, but we also have omega square omega c square here times alpha square. So I can write it this way: plus alpha square minus 2 times omega square omega c square. Well, if I want to get to this format, I need to get rid of this component here. So if I set alpha equal to rad2, this goes away, and as a result what we get is this value. So we get then exactly with that setting, we get the squared of magnitude of response, omega c to the power 4, and then we get let's say omega to the power 4 plus omega c to the power 4, which if we factor out, if we divided both numerator and denominator with omega c to the power 4, we exactly get what we want, which is 1 plus omega over omega c to the power 4, and that's exactly the kind of a magnitude response that we want to get for a second order Butterworth filter. So in summary, I need this. We need to definitely set omega to alpha equal to rad2 to get what we want. Here is a reminder that if we want, for example, to use an op-amp, thanks for earlier recommendation and suggestions, OPA 1656 op-amp from Texas Instrument is a very good ultra low noise and low distortion FET input op-amp. This one is a dual package, so there are 2 op-amps in this package. So this is an example of a practical choice for reasonable frequency range. This is relatively a high bandwidth, high gain bandwidth operational amplifier with low offset and low noise. So there are 2 op-amps in this package. So if, for example, we need 4 op-amp in this kind of example, then 2 such needed, or you can go with a quad package. So that's just an example. Now let's go for the last section of this or segment of this example, in which we want to find the value of these components to achieve, say, 500 kilohertz 3 dB frequency. So to do that, I'm going to just say, okay, omega c is 2 pi fc, and desired is fc is 500 kilohertz. So therefore omega c is 2 times 501 meg, so effectively becomes basically just 10 to the power 6 pi radian per second. So I want, and at the same time, omega c, as we set it, omega c is just 1 over RC, where R is the main resistor in the circuit and C is the value of these 2 capacitors. So I can say, therefore, omega c is equal to 1 over RC. Let's set C to a very reasonable practical value of 100 picofarad, which is 10 to the power minus 10, and let's find R. So you can change this, of course, to some other value, but the target is finding R in a reasonable range that matter or is reasonable for the specific implementation. So we get 10 to the 6 pi radian per second equal to 1 over R times 100 picofarad, which is 10 to the negative 10. So if we solve this, we get R equal to basically just 10 to the 4 divided by pi, which is roughly 3.18 kilo ohm or 3.2 kilo ohm. That's a reasonable value. So if you want 10 times less than this, you can then play the game and let's say increase the value of cap by 10 times. If you want 10 times more than this, then you can play the game and reduce the value of this cap by a factor of 10. So that's how we play. And now that we found R, we can go back to what we set in the sense of what is R2. R2 is R over alpha, R2 is here, R is here. So I'm going to find the value of R2. Now, knowing that I'm realizing a second order Butterworth filter that requires alpha here to be rad2. So I need alpha to be rad2. As a result, I am going to say R2 is R over alpha, and we know alpha is rad2, so alpha is square root of 2. Therefore, R2 is simply, in this example, 3.18k, which is the value of R divided by rad2, and that is equal to 2.25 kilo ohm. So 2.25 roughly kilo ohm. So therefore, if in this circuit we set the values of cap, let's say 100 picofarad, R 3.2 kilo ohm, and R2 2.25 kilo ohm, and with the let's say op amp, the Texas Instrument OPA 1656 dual let's say package op amp, or if you want just one op amp, that would be 1655. So this is Texas Instrument or TI op amp. So if we set the value of the components like this, if we select properly the op amp that we need, then the circuit will be ready for test and implementation. And this is realizing a second order Butterworth filter, and the transfer function from V in to V out is what we found over here with alpha equal to rad2. So the transfer function is just in the example that I just solved. Basically, h of s is, so omega c squared is going to be 10 to the 6 pi squared. So that will be 10 to the 6 pi squared. That's omega c. And then s squared plus we had alpha omega c. So that would be rad2. That would be rad2 times omega c. And plus again omega c squared. Okay, so I hope that this example is helpful in terms of showing how we can realize and implement in one example implementation the second order Butterworth analog filter as a low-pass filter. It's a low-pass filter implementation with this sort of a magnitude response, of course. Of course, it's possible to use combination of second order Butterworth like this implementation, or another variation of it with a first order, to use cascade of them to implement higher order Butterworth filter if need be. I hope this is helpful. Thanks for watching.